Thank you very much, Valeria, for your very kind introduction. Good afternoon, everybody, wherever you are. Some people may be still in the morning if you are connecting from Western Canada. I hope you have a great day. I also need to apologize because of this technical issue that a little bit of bottom of my presentation is cut. So today I would like to speak about not a very recent, the work that has been concluded a year ago, 2 years ago, in fact, on changing natural stream flow regime. This work has been done by a, so I don't know why it is not moving forward. So this work has been done by my former PhD student, Dr. Masoud Zahirpour, as a chapter, and has been formulated as a chapter in his thesis. And this chapter is also published in 2021 in HES by the name of a global algorithm for identifying changing stream flow regime, application in Canadian natural streams from 1966 to 2010. I would like to recognize Masoud's dedicated work to this study, and what I'm actually presenting today, I want everybody to recognize that this has been the driving force behind that has been a dedicated PhD student. So let me actually bring up the problem that we have. So we know that during the Anthropocene, the current geological epoch that we are living, natural stream flow changes due to multiple reasons. You know, one reason that actually we're going to specifically talk about that would be about climate change. We know that the climate change, because of changing that's induced into hydrological processes, basically result into changes in the river flows that we have, and we are able to monitor those changes in various parts of the world. However, human intervention also is another main important factor for change in the stream flow regime. You know, human has changed the landscape in the last 150 years quite drastically, and those changes in the landscape would change the runoff generation processes that then we will see them at some point and some point in time and space in the streams. We also have started to severely regulate the stream flow regimes by making dams and dikes and other in-stream infrastructure from which we are able to supply our water for food and energy production. So, however, we need to recognize that those changes, on one hand, although it brought us socioeconomic development, on the other hand, change the characteristics of the river flows that we have. So in this presentation, I forgot about human intervention. I'm not talking about the human intervention. That's completely a different ball game. And I basically focus only on the effects that the climate change can have on natural stream. It means that the streams that are not disturbed by human activities. So when we are looking at those changes, those streams, particularly in Canada, we are also recognizing that we are seeing some changes in the flow regimes, and that has been recognized from, I would say, late 1980s, when people start showing and demonstrating that we have changes in the Canadian stream flow regime, mainly on those parts in northern Canada. So the studies that has been so far has been done attributed those changes partially to form of precipitation that we are now, everybody agrees who lives in this country long enough, we know that we are receiving less snow during a year, and our precipitation shifts to the rain. However, the amount of the precipitation is also changing, not only the form, and also the hydrological processes changes because of the warming. For instance, we have several melt events during a winter season, and we have maybe intensified evaporation because of the warmer temperature. So all of this is gonna represent and manifest itself into the stream flow. So basically, when we look at the stream, we are seeing the combination effect of all these changes that is actually captured in the stream flow hydrograph. So basically, when we want to look at it, we will realize that first of all, a stream flow regime is constituted by multiple stream flow characteristics. So there are multiple dimensions that are defining the stream flow regime. So basically we are dealing with multiple characteristics that we need to deal with. The other thing that actually we understand by looking at the stream flow regimes across the world, not only Canada, we realize that stream flow changes in the landscape rather in a gradual way than sharp. So we are not having some sort of, if we have different stream flow, we are not able to make a crisp and sharp distinction between the stream flow regime, and rather the stream flow regimes are somehow intersecting together at some regions, and we are clearly seeing that into a landscape. So for instance, when we are transiting from the high mountains to the foothills and then to the prairies, for instance, in Western Canada, we are seeing that actually the hydrological processes gradually changes, and therefore the stream flow regime also gradually changes. So there is a huge point that what is the point of distinction, let's say, from a glacial regime to a stream flow, to a snow dominant region. And that is actually, we're gonna see that when we are going into the landscape, those things are happening quite gradually. So if it is happening gradually, then we are able maybe to define a level of association that would be able to mention the degree of belongingness of a stream into different particular regimes that they might not be completely divided from one another. Not only the stream flow regime itself is constituted by multiple stream flow characteristics, but also multiple processes are causing these changes. So then we are dealing with multiple attributes that might cause the changes in the stream flow regime that we are observing. And last but not the least, not only the stream flow regime changes gradually over the space or over the landscape, but also when we want to study the changes in the stream flow regime over time, we are also seeing that these changes are rather gradual. So how we try to actually approach this problem, because in the previous problem, distinction between flow regime has been considered rather sharp. So for instance, we had a stream flow regime, either it is snow dominated, or it is rain dominated, or it is glacier or snow dominated. So basically we had a quite distinction. So here we try to, and then there are few stream flow characteristic has been considered to capture the change. Some studies that focus on the high flows, for instance, only use the high flow characteristic, for instance, the timing of the peak and the amount of peak flow, or on the other side of the spectrum, some other studies try to look at the low flows, and they consider those low flow characteristics. And we are seeing that there are little studies that consider everything all the information that are happening in the hydrograph. So basically, the first thing that we defined here, we assume that the regime is identified by the characteristics in the stream flow hydrograph. And we identified 30 different characteristics from which we are able to infer the stream flow regime. What are those? 12 monthly values that we have in the long-term mean, monthly mean of the flows. Also the timing of the peak, timing of the low flows, and also the annual volume. And also, if we have a multiple years of data, we are able to also look at the variability of them. So the first moment and the second moment of the 15 characteristics, monthly, 12 of them are monthly flows. 2 of them are timing of the peak flow and timing of the low flow, and the 15th one is the annual volume. So we are considering first moment of these, 15 first and second moment of this, so we're gonna have 30 attributes. Okay, so the second assumption that we did, based on the brief intro that I provided in the previous slide, is that the distinction between regimes are rather gradual. So the flow regimes can intersect each other. So we might have a flow that is basically both snow flow regime and glacial snow regime. So that is okay to have a joint condition that we have a stream that is belonging to 2 or more stream flow characteristic. The other one is that we have a regime shift, this regime shift should, and if this regime change is climate induced, then we need to observe that gradually, not as a sharp distinction in the regime. So based on that, we try to look at the stream flow in Canada. So we only focused in natural streams that are available in Canadian HYDAT data set. And we try to look at the different time periods. And the purpose was that find the time period in which we have the longest data period. And also we are able to look at every drainage basin and every key catchment within this Canadian drainage basin. So based on that, we converge into the data period of 1966 to 2010 with 105 stations across all the catchments and major basins of Canada. Okay, so in order to pursue the way that we wanted to go, so we say that, okay, so we have a bunch of stream flow characteristics from which we are able to cluster stream flows and understand how many regime types we have. And then we would be able to through a formal trend analysis, we would be able to understand how much we are having the change in the membership, from which we are able to infer the amount of regime shift. And then we would be able to understand how this regime shift is basically attributes into the changes that I have in my stream flow characteristics. Remember, we had 30 stream flow characteristics are considered. So now if we are observing that the regime is shifting, why the regime is shifting, which characteristics are changing that from which this regime shift is induced. So now, if I want to look at the methodology, I have 3 steps. First of all, I need to classify the stream flow regimes. When I classify them, I need to monitor their evolution in time in order to understand how the regime is shifted. And then at the end, I need to somehow attribute the changes that I'm seeing in the stream flow regime into the stream flow characteristics from which the stream flow regime was inferred. So let's go into that one by one. So in order to cluster the result, we use a fuzzy clustering algorithm. So fuzzy clustering algorithm inherently accept that the clusters or the categories that we want to classify a bunch of data into can be intersecting. So for that, basically, we have intersecting clusters. However, the sum of membership to all clusters should be 1. So basically, if you have a stream, the stream can belong to all of these flow regime that you identify, but the degree of membership, the summation of degree of membership of belongingness to the regime should be 1. And we want to basically minimize the degree of dispersion that we have in classifying these data points or streams. So if we are solving this problem, this is identify an optimization problem. And if we optimize this optimization problem, we're going to converge to a set of cluster center. And if we have the cluster center, then we would be able to attribute and understand the degree of belongingness to every membership. So I'm not talking about the mathematics of that more than this. People who are interested can ask questions or refer to the original published paper in which we are presenting these things quite clearly. So the good point of the fuzzy clustering is that because the summation of the membership should be 1, so if the membership to one regime is increasing, it should necessitate decreasing in the membership in another regime. So if I'm actually approaching, let's say, toward a certain regime, this means that the belongingness to other regimes must decrease. So from which we are able now to have a framework that addresses from what regime we are transiting to what regime by just monitoring how the clusters, the membership belongingness to the clusters are increasing. So I can do a clustering, let's say in the first instances of the data, then I would be able to change the window in which I'm looking at the data. And then I would be able to recalculate the degree of membership. So when I actually do that for the whole time series, then I'm going to have a time series of the degree of belongingness. So now I'm seeing that, for instance, to this cluster, the degree of belongingness is increasing. This means that to the other cluster, the degree of belongingness should decrease. So if that's the case, then we are able to understand how the regime is shifting. And then if we are understanding the regime shift, then we are able to look at it simultaneously with changes in the stream flow characteristic with which we inferred the regime. And then by looking at the dependence analysis, we would be able to understand the changes that we observe in the regime shift correspond with changes in what stream flow characteristic among those 30 characteristics that we considered is resulted from. So if we are combining now this methodology, we're gonna have a methodology with which we are able to understand the stream flow regime based on the long-term annual mean and the variability around that. We are able to understand the shift in the stream flow regime in the hydrograph, and we are able to understand if we are having a regime starting from one condition in 1966, how through time it has actually went to other flow regime, and changes that actually resulted this transition is induced by changes in what stream flow characteristic. So we are actually now having a combined and total framework from which we can start from classifying the flow, understanding how the regime is changing, and then attributing that into changes in the stream flow characteristics. So let's go and understand what we have here. So fuzzy clustering is an empirical method. So first of all, we need to assume a number of clusters, do the clustering, and see how the clustering look like, and repeat that with a different number of clusters as a priori to understand which actually clusters provide us the best goodness of fit. So we have done in a study, we started from 2 clusters and go up to 10 clusters and try to see how my convergence is improving. And we realized that this number of 6 clusters provide me a golden number of clusters with which I would be able to cluster the stream flow regime, the 105 streams that I have across Canada. So when we are looking at that, we realize that the center of those clusters are identified by some streams in Canada. And by studying those streams, we were able to somehow name those mathematical clusters by some regime types that have hydrological meaning. So for instance, the first cluster refer to stream flow responses that are slow, and they are the peak happening in the warm season. This is glacial regimes, for instance, and the flows that are in northern Canada, connections between rivers and big lakes. And we are able also to look at the other clusters and identify what kind of hydrological regime they are inducing. So when we are looking at the clusters, so now when we are looking at the first in 10 years decadal 10 years, and then the last decadal 10 years. So the first one is identified by the gray and the last one identified by the pink. We are seeing some changes in the stream flow regime. So if we want to understand how this, so when we do the clustering and changes, we can actually look at where geographically those streams belonging to each of these clusters are located. And we are seeing that they are nicely geographically located, and we are able to identify them geographically. Then we are able to look at the changes through the Senate slope. So if I am monitoring the membership function at every 10 years, how this membership function changes in time, and I would be able to understand whether these changes are significant or not significant, and what is the sign of that. So if I do this exercise, then I would be able to understand how the regimes are changing for each of the streams that are belong to each of the categories that I identify. And I would be able also understand from the joint changes, because as I mentioned, increasing trend in one membership function necessitate decreasing trend in other membership function. So from this, I would be able to also measure the degree of departure between the memberships as the time goes on. And if I'm able to do that, then I would be able to come up with maps like that, that telling me each stream flow in Canada, how, if they have a specific stream flow regime between 1966 to 1965, 75, how they are moving into a new state that is going to be a different clusters. So if we are doing that, then we are able after that to understand how this regime shifts. So in every streams, I have a dominant regime shifts that is identified by the largest departure that I'm seeing between the trends. So now I would be able, by attribution through the dependence analysis, I would be able to understand how these changes, this regime shift is attributed into the decreasing or increasing changes in my flow characteristic. I had 30 flow characteristics. 15 of them were the first moment of the 15 characteristics, and then the last 15 one was the second moment of the characteristic I consider. And I would be able to understand this regime shift is induced by what changes in stream flow characteristics. But the study that we have done, there was some assumption. First of all, the result that I showed you was only for decadal time scale. So there is a question that if I change the window with which I'm looking at the data, let's say to 15 years or 20 years, what would be the changes in the result? The other issue that actually is there is that I use the first 10 years of the data, 1966 to 1975, to initially cluster my data. The question is that if I change that episode with which I'm clustering the information, clustering the stream, again, what would be the changes in my results? So in the left-hand side, I try to cluster based on different time episode in my data. So I consider all the possible time episode in that 45 years of data, and try to see if I look at every 10 years, how much the center of the clusters that I identify would change. And I realized that the things are, perhaps are converging. So even if we are changing the time episode with which we do the clustering, we are coming to a nice cloud that are separated from the other clouds. So it seems that we are converging. That convergence is not induced because of the particular time episode I consider. The other thing is that if I change now from the 10-year decadal window to 15 years or 20 years, again, am I going to change my clustering result? Going to change? And we realize that even if we change the length of the window with which we observe the data, again, it seems that we are converging to the same region of clustering. So it seems that the clustering is tight. The other issue is that, okay, so I inferred all of this result from the decadal time series. The question is that if I now change my window again, am I going to see the same regime shifts? Am I going to see the same reasons for changing in the stream flow regime? So basically, we repeat the experiments with 15 years, with 20 years, and we try to see whether we see any dissimilarities. And what we observe is that we are actually having above 70% at least similarity between the result when we change the window size. So when we transcend from 10 years to 15 years and then to 20 years, from all the result of the regime shifts and attribution and all these things that we have done, the results are actually, for most of the cases, above 95%, the result would be similar. In some cases, I have less similarity, but again, all of them going to be above 65% of the similarity. So it seems that we are actually detecting something real, that if I change the time episode, if I change the length of data, again, I'm seeing the same thing. So the last question that we raised is that, okay, so now we attributed this regime shift over 105th station. If I now bring new station, am I gonna be able to infer to the same result? So basically, if I do out of a sample validation with streams that was not used in that exercise, am I gonna get to to a result that are consistent with the previous result? And what we have done, we picked up 9 stations from the Canadian prairies, which we didn't have any station on that 105 station that we considered. The reason that we were not choosing those, because they were actually getting into another data set outside of the 1966 to 2010. So we brought this data, difference in the region, difference in the data length, and we tried to see whether the clustering result can be relevant to those as well. And we realized that, yes, it can be relevant. And we are actually detecting the regime shifts that we were expecting to see in the prairies. So it seems that not only work with different time episode, time scale, everything, but also in a different region, still in Canada, that we have not used for the clustering and attribution study. However, again, the question is that we were not the first people to look at the Canadian stream flow regime changes. Multiple people, some pioneer hydrologists look at these processes, and they come up with a lot of literature around those areas. So the point is that now that we have done a consistent study into a deep particular time episode, are we able to verify some of the results that previous researcher has obtained? So we actually presented a very dense figures to classify the changes that we are seeing based on the literature in stream flow regime. So some of those we are able to observe them again. So we reconfirm those changes. However, because our methodology uses all the information in the hydrograph, and we don't discriminate between the first moment and the second moment of the flow characteristic, we don't only consider low flows or high flows, we consider every information in the hydrograph. We were able to also discover some changes in the stream flow characteristics that previously was unseen in Canada. So I don't want to waste the time, because I know that it's the time for questioning. So I invite people to go to the paper and study this table, which actually is our fact sheet that how the regime is changes across different major drainage basin in Canada. I'm hearing only showing the result for the Pacific drainage basin in Western Canada. Okay, so let's wrap up, and I would be very happy to answer the question. So I'm happy to say that Masoud's work was the first consistent, both temporally and spatially, pan-Canadian study to understanding climate change-induced changes in stream flow regime. Why I'm claiming it was the first consistent temporally and spatially, as I said, there are multiple works before us. In fact, perhaps more than 100 papers from late 80s till now that working at the stream flow regime in Canada. However, some of them, they were not completely covering all the 4 major drainage basins in Canada. The other thing that actually was there in the previous study, none of them had the same temporal resolution. Therefore, a comparison between changes in different parts of the Canada was not possible because the data was from different periods. In this study, for the first time, we did a study that covered all parts of the Canada and also is temporally consistent. The algorithm that we presented is actually a globally relevant algorithm. In fact, we are now using this algorithm in order to classify the global stream flow in 4,000 more than 4,500 station natural streams that we have throughout the world. The data is from a global runoff data center. Although we were able to make the attribution, however, I should remind people that we attribute the changes, the regime shift, into stream flow characteristics. However, we know that the stream flow characteristics themselves are changing because of changes in the hydrological processes. So the question is that what changes in hydrological process created this stream flow regime? This delineates is a much more difficult problem that perhaps requires us to basically continue this work, and I hope graduate students as well would be able to break through to some of the potential solution. So thank you very much. And this work and the paper that we actually published is dedicated to the memory of Richard Jankovich. He actually passed in 2018, and many of the discoveries that we have about the stream flow regime change in Canada is owes to his studies, particularly in northern part of the country. Thank you very much indeed.